Hello, everyone. Are we up? Yep. So I'm Owen O'Malley. I'm one of the co-founders of Hortonworks, and we're here to talk about adding ACID transactions with insert, updates, and deletes into Apache Hive. Alan Gates is also giving half the talk, so he'll be up here in a little bit. We've both been working in Hadoop for a long time. I've been working in it since the beginning, and Alan, when did you start? 2007? So it's been a while. I guess I should put that up for you guys to get our Twitter accounts. But what's the problem we're trying to address? The problem is that Hive only has one mechanism effectively for adding new data in, and that is updating things at the partition level. You can technically do inserts, but mostly people do insert overwrites. And that forces you to do a very particular layout for your tables. You end up setting up your partitions at the granularity you want to do updates. So extremely often you see partitions for days. I've even seen partitions for hours or even half hours, because as the data comes in, you want to write a new partition and then add it into Hive. So that works great for inserts, right? Because you can write the data into HDFS, do the update, and add the partition, so it shows up as a single unit, right? There's a single transaction that adds the new data. But if you have to restate data, there's no good way to do it. If you do an insert overwrite query, Hive actually is deleting the old data and writing the new data as part of a job. So any queries that run in the middle there read inconsistent data, and that's really unfortunate. And finally, there's no way to insert, update, or delete individual records, right? There's no insert values, there's no delete statement other than delete a whole partition. And that really makes ad hoc queries difficult. I don't know about you, but when I started with Hive, the first thing I looked for was insert values so I could put a few values into a test table. There's no way to do it. You have to have a file and load the whole file. It works, but it's very cumbersome, and we'd like to make it more standard. Actually, that fits in with a theme that we're doing in general on Hive, which is making the SQL language that's supported by Hive more standard. Okay, so why is ACID an important property? In honor of Amsterdam, I was tempted to make this slide, why is ACID important, and make it tie-dyed, but I went for the very boring look here. Hadoop has never had ACID properties. It's always been viewed as part of a trade-off for performance. But your data isn't static. You don't load it once and then keep running with it. It's continually changing. So it's not very realistic to say, load up all your data and then start running Hadoop on it. That's not the way you want to work with your data. So currently, users do a lot of ad hoc solutions to try and make this work, but it requires a lot of work on their part. We want to incorporate this into the framework and make it part of standard Hive. And finally, there's the quote from Yoda, who I always liked. With ACID, your updates either happen or they don't happen. There's no part happening, right? You don't try to make it happen. It works or it doesn't work, and that's important. So what are the use cases that we're looking at? The first one is the one where you're updating a dimension table, right? You have a bunch of addresses for your customers that have been updated, and you batch them up once an hour, once a day, and you want to make the changes, right? That's currently a pain. You have to rewrite the whole customer table. With the ACID work, that will be easy. You'll just issue the update and make the changes. Or you want to delete a customer, right? They come through and say, we'd like you to delete all of this data for my account. I don't want you to have me as a customer anymore. And for regulatory reasons, you actually have to go through and delete it. Again, that's not easy right now. You have to rewrite the partition without them in it. Finally, there are some people that when something goes wrong in the computation, they need to go back and restate a bunch of data because it got messed up by the processing. And so they need to make changes to the fact tables. And the use case that we're actually addressing first is streaming ingest, where you have this flow of data coming in from Storm or from Flume, and instead of just writing to HDFS and then once an hour adding the partition into Hive, you want that data to become available when as soon as the transaction completes. So every 30 seconds, you can have the Flume agent that we're writing commit your data, and so as the data flow comes in, you see it 30 seconds later. That's a huge improvement over having hourly partitions and only seeing it at that level of granularity. All right, now obviously we're not rewriting HDFS. We're not making HDFS so that we can rewrite files. So we're using a base file and having additional files that are updates. That lets us use HDFS, and you just write the updates as you make the changes to the data. When we go to read, on the other hand, then we stitch them together. Since the two files are sorted the same way, it's just a merge sort, and we can quickly put them together and give Hive the latest value of the record without bothering it with the intermediate values. Now, one of the pieces that we need to manage, of course, to do this is that we need to have transactions, right? We need to have a concept of transactions. So when we want to write new data, we need to get a transaction, and all the data that it writes will get tagged with that transaction. So until that transaction's committed, no reader will show the user any of that data, even if it's in HDFS. Readers, on the other hand, get the list of committed transactions, and they filter which files they look at and which rows they present based on that list of committed transactions. That has a lot of nice properties. That means that your readers never get blocked on anything, right? They don't get blocked on transaction, on commit happening from a writer. They don't get blocked on the compactions. Nothing blocks a reader, and it always gets a consistent view, right? When at the start of the query, it takes a snapshot, and that's all it will see until that transaction completes. And that's a really nice property to have. So what does it actually look like? If you see here, we've got the base file with some data. Then down in the second part, we have an update where we insert a row, update a row, and delete a row. And then we get a second update where we update, and delete. And then the reader stitches them together so that it just gets a virtualized view of the result with the last update from each record. What does this look like in HDFS? Because of course Hive is still storing in HDFS. We left the partition locations alone. So Hive stores things as the database, then the table name, and then the partition name. And we're still having the same structure. But instead of just having files at the partition level, now we sort the bucket files into directories based on the transaction IDs. So the transaction IDs for the base files will say the partition name, then the base, and then the transaction ID, and then the bucket. The delta files, on the other hand, look like delta, the beginning transaction ID, the final transaction ID, and then the bucket. All right, so this is all hidden under the hood, but it's important to understand that we did it this way so that you never get blocked, right? Compactions don't blow out the reader. The reader will continue to have the data available to it. in spite of the fact that there may be a more up-to-date version of the file that gets written later. Minor compactions, where you merge deltas, take a set of deltas and merge them into a single delta file. That's just getting rid of files so that you can read one file instead of 10. And major compaction, of course, takes all the delta files and the base file and merges it into a new base file. So the TID on the base directory is really about which transaction did the compaction for the base. Now, to do this, there are a couple of different pieces that we had to add, and I'm going to talk about the input-output format, and then Alan's going to talk about the compactor and the transaction manager. So we created a new interface because Hive is agnostic to input formats, and so we wanted to preserve that characteristic. And so we created this ACID input and output format. And the unique key is the transaction ID, the bucket, and the row ID. The reader just returns the most recent update. I had to add a raw interface for the compactor, and we implemented all this with ORC, so that if you use ORC, you can get these characteristics, and other formats can be added later. Now, one of the critical pieces is that you don't want to lose your capability of sharing the work between mappers, right? One of the important characteristics of Hadoop is that it can divide files into parts and have different tasks work on the different pieces. So it was important that when you slice the base into different parts, that you read the corresponding parts on the delta files. So the way it works is that in the base file, you find a key range, and then you use that key range when you're reading the deltas. So that the deltas, you only see the deltas for the key ranges that you're interested in. OK, and with that, I'll switch off to Alan.
All right. Hello, everyone. As Owen said, I'm Alan Gates. I've also been working on Hadoop for like a long time, and I'll talk about the transaction manager and the compactor and a little bit about kind of how we're rolling this out and when you'll see different parts. So first of all, we need a way to keep track of transactions now, right? If we're going to have transactions, we have to have some place that's coordinating them. In addition, we need to integrate locking with the transactions. When a query is going to read something, it locks that file. Or, well, actually, let's do the update case. If it's going to update a partition, it's going to get a lock to do that update. That's part of a transaction. When you commit or abort that transaction, it needs to atomically unlock that as well, right? So these pieces need to be integrated. So we knew we had to set out and write a transaction manager and make the locking system work with it. Now, Hive already has a couple lock managers. It has one in memory system. That's great for testing, but obviously it's not durable in the face of failures. So we didn't consider that to be an adequate option. And it has a Zookeeper one, but Zookeeper, we weren't super excited about requiring yet another component to make something work with Hive. Plus, it didn't have some of the performance characteristics we wanted this to work with. It made it harder to integrate with the transactions. So we decided to take the lock manager interface that already existed and add a database-backed instance of it. So it didn't take too long to thinking about this to realize we sort of have this database lying around in the form of the Metastore that already gives us very nice ACID transaction or ACID semantics. So it makes sense to store the transactions and the lock ID in there. It's also very useful because Hadoop has no shared clock, right? So one of the things that's key about a transaction is everybody has to understand what's the ordering of these transactions. You have to have that in order to know how to whether a given reader should see a given transaction or not. And since there's no shared clock, you can't depend on a timestamp for that. Using the Metastore database to generate our transaction IDs and our lock IDs gives us that sequencing without trying to put in some super sophisticated clock server to make sure that everybody has the same idea of what time it is. All right, so what is our transaction model? Just to be clear here, in the very first release, there are transactions underneath in the way it works, but there's no ability for the user to say begin transaction or commit or rollback. That'll be in a future release. I'll cover a little bit more of that later. The isolation level in this transaction model for now is snapshot only, so that means when a reader starts a query, he will get a transaction ID, a list of what are the valid transactions at this time. Actually, it's the other way around. He gets a high water mark and then a list of transactions under that he should ignore that are either open or aborted. And he sees those consistently throughout the life of his query. So you're guaranteed that whatever you start with is what you see for the whole time. And then we've also added a new show transactions command so that the user can actually see, or somebody like an administrator can see, what are the current open transactions. I can get an idea of what's going on in the system right now. And we also had to extend the locking model a little bit. Hive had, as I said, it had already a couple lock managers. It had just exclusive and shared locks. Turns out we actually need 3 types of locks to make this work well. So there's shared locks, pretty self-explanatory, and exclusive. We also needed the notion of a semi-shared lock, which the idea behind a semi-shared lock is semi-shared can share with shared locks, but it can't share with other semi-shared. So it alone can hold that part of the lock, and I'll explain why we need that. So select and insert can work with shared locks. Why select works with shared locks is obvious, right? You can have as many readers as you want at a time. Since Hive doesn't have any uniqueness constraints, it has no primary keys, insert can always be shared as well. There's no conflict in multiple writers pouring records into a partition or a table at the same time, because they can't conflict. Update and delete is where we need semi-shared locks, right? The notion here is we don't want multiple users updating or deleting a partition at the same time. Now, let me explain why we did this. You could go with that being an exclusive lock, which would be safe. You'd only have one person writing into it, but then you'd be blocking readers, which you don't want to do. Since we have transactions, since we know the transaction IDs of the writers and the readers know what they can read, it's safe for readers to be reading this data at the same time that writers are updating or deleting it. So there's no need there to block them off, so exclusive would be too much. You could do it with a shared model that is more traditional in an OLTP type database, but then you have to deal with all the deadlock detection, plus, did 2 people write on the same row, and who do I choose to lose in that situation, those kinds of issues. Since we're not aiming at OLTP as a use case, so that's not our goal, it made more sense to us to be safe and just say, okay, we can only have one update or delete operation going against a partition at a time. The second update or delete will just hold until that lock's been cleared, and that way they'll also get a consistent view, because when they come to read, they'll see what's already been updated or deleted. All right, so this depends on having something to do compactions in the background, right? As we've talked about, each transaction, or in the streaming ingest model, each batch of transactions creates a new set of deltas, right? A new delta directory with a set of buckets inside it. And as we all know, too many files makes for an unhappy name node. So you can't just leave that as the way it is, right? That each time somebody comes in and makes some change to the table, you get a new file. So we need a way to compact this. And there's a couple kinds of compactions. One is to just collect multiple deltas into a single delta file, or single delta directory with a set of buckets. We call that a minor compaction. And then there's also a point where you need to go through and rewrite that, the base and delta into a wholly new base. And the question is, why do you need to do that if with a minor compaction, you're solving the number of files issue, right? Now you have a base and a delta, 2 files per partition. That's not that bad, or 2 sets of files, really, because each is a directory with buckets in it. But 2 sets of files per partition, that's not that bad. But the issue is, over time, as more and more changes are written into that partition, the base is becoming more and more out of date. You can, if you want to think about it this way, it's getting holy, right? There's lots of gaps in it that are because of updates and deletes in the delta file, and so it's more efficient to actually rewrite that so that the reader doesn't have to spend more and more time reconciling those differences. So here's an example, really straightforward, of what a minor compaction looks like. In the first example here, you see what's your partition look like after you've written some data to it, done some updates, but you haven't yet compacted it, and then on the bottom there you see what happens after the compaction. So as I said, it's just collapsing these deltas together. We run this automatically when there's 10 or more delta directories, and that's configurable, but 10 is the default there of how wide we let that get before the system kicks that off. And just to be clear, this is all being done automatically in the background. You as a user don't have to pay attention to this and go, oh, it's time to go compact. The system will figure that out and run the compactor for you. For a major compaction, see this a similar thing. You've got a base file, you've got a set of delta files, and then when you're done here, you just have a brand new base file. No delta files now. This is run when the size of the deltas taken together are at least 10% of the size of the base. And again, it's configurable. You can turn that up or down depending on what works well for you. So as I've said, this is all automatic. The Metastore actually watches these things in the background and schedules the compactions. You can initiate a compaction event yourself if you want to. There's a new alter table compact command that will allow you to initiate either a minor or a major compaction. You can choose that. You don't need it unless if you're finding that you need to use that a lot of time, it probably means you need to configure your system a little differently so it's compacting at different times. But it's very convenient for testing and those kinds of things. And you can actually, if you don't want the system to compact your table for some reason, if you want to take control of that, you can set a property on the table to say, don't auto-compact this, and then the compactor will ignore it, and you can fire compactions as you want. We don't lock a partition while we compact it. We allow reads and writes to go against the partition while compaction is going on. That actually all works fine. Any new data that's being written into the partition while it's being compacted will be going in a new delta file that the compactor will ignore. Reads go against the old files that are still sitting there. The system knows how to manage the difference between manage the fact that the old files are still there. Even after the new files have been written, readers that were started before the compaction can still access the old files. In fact, actually, is this on the next? Oh, nope, sorry. In fact, the last step of compaction is for a cleaner thread to come along and remove all the files that now are no longer needed, but it's actually aware of the readers. So you don't have to worry about, oh, the file's going to vanish on my reader because a compaction is going on. It will wait until all the readers who are reading that data have finished with it and then come clean it up. Yeah? Yeah, sure. If there are bugs in the compactor, you can lose transactions. Just like if there's bugs in anything else in Hive, it can blow your data away. And then you can show what compactions are going on by doing a show compactions command. So that will list what's currently being compacted in the system. All right, so how are we rolling this out? In phase 1, which will be in Hive 13, it's actually mostly checked in. There's 1 or 2 more patches to check in, but it's mostly there. We've added the transaction and lock manager. That's in the changes to orc are in to make this work. The compactor is almost there. The patch is up, but it hasn't been checked in quite yet. And then, as I said, we'll have snapshot level isolation in this. We haven't yet done the language integration for things like insert values, update, delete. Our plan is to get that done in the next release of Hive. I just put the we hope here on Hive 14 because, future, let's see, we're quoting Yoda today, so the Yoda quote for that is always in motion the future is. That's our plan, we'll see. But we want to do the actual support for update, delete, insert values, and then also full cross-query transactions. So you can begin a transaction, do a set of queries, do a commit, or a rollback as appropriate. In the future, we'll look at adding additional isolation levels, such as dirty read or read committed, and the SQL merge command. This is really based on user feedback. If nobody says they want this, we're not going to run out and do it just for completeness sake. But if we start getting a lot of feedback that, hey, I really need dirty read, or hey, I really need this other thing, then we'll look at adding that in. All right, so limitations of the system. Hopefully we've said this enough, but we are really focusing on data warehousing here, not on OLTP. If you try to do a lot of transactions quickly on this, it will be bad. We're not aiming at that. We don't view that as Hive's strength. We don't think it makes any sense. And the way we designed this, it would be a total fail if you attempted to do that. And the table must be bucketed. And for the moment, it can't be sorted. That's just a limitation of the work we've done so far. Hopefully, we'll remove that fairly soon. All right, so in conclusion, 4 questions. If you want to see more information about this, there is a JIRA on Hive's JIRA for this, Hive 5317. I strongly encourage you to go watch this JIRA, and here's why. Because as far as we know, the most watched JIRA in the Hadoop ecosystem was the Yarn JIRA, MR237. And it had 109 or something, 100 and something like that watchers. And we realized that one day that we had 107 or 108. We were just behind the Yarn one. So we did a little clandestine operation, like I went and unwatched the Yarn one, and I think Owen did too. And so suddenly we were ahead of them until we opened our big mouth, and Vinod, who sits right next to me, got his whole team to go unwatch ours and watch the Yarn one. So we've got a little contest going. We're 2 or 3 behind at the moment. I strongly encourage you to go click the watch button here. All right, so the rest of this we've covered. Adds ACID semantics to Hive. We'll add full insert, update, delete, and all still at scale. All right, and with that, I will open it up to questions. Please come up to the mic, I think, if you want to ask questions, because otherwise it's really hard to hear.
Hi, I have a question regarding the OLTP support in future with HBase backend or something like it. Do you have any?
Okay, so I'm not on the HBase team, so I don't 100% know. Oh, you mean through Hive with HBase? I don't think so. I mean, I'll preface that by saying I can recall standing on a stage a few years ago and saying Hive would never have update. So not only was I wrong, I'm the one who's making myself wrong. So who knows? But I will say that HBase is pursuing, I don't know if you've heard of the Phoenix project, where they're putting a SQL front end on HBase. If there were going to be a place to do OLTP type stuff, I would expect that would be more likely to be it, but I don't know for sure. Yeah. Yeah, there's some commercial attempts at that, but I haven't looked at them, so I don't really know.
Well, and of course, with HBase, you don't have transactions cross rows, right? You get updates to a single row if it happens or not, but you don't get cross-row transactions. Yeah.
My question about about the state of this patch. Is it possible to backport it to current releases of 0.12 versions for Cloudera and Hot-on-Walks?
13 is coming out really soon.
Yeah. Well, the big thing is that it depends on changes in org, right? But I don't know if
No,
you're...
actually, the Metastore changes are probably... We're
Well,
both
but if
pointing
you
at each
took all
other's
the-
work and saying yours is going to be hard to backport.
Mine's easy for.
So it's mainly depend on org. So it's wall semantic fully depends on org and
Well,
can work
no.
with Parquet, for example.
We introduced a new API, right? We didn't make we're not going to make the core of Hive depend on any particular input format. So if someone does the work to make Parquet support this, then it'll work with Parquet.
So it's pluggable. Yeah.
So it's pluggable.
The only requirement is that the file format has to have a row ID because it has to understand how to merge together the base row and the delta row, right? So you have to have some notion of how would I do that, which a row ID or some equivalent
Well,
is
and one of
required.
the challenges with Parquet is they don't have indexes, which
and
Orc
can
does.
slice.
So you can't jump very effectively to spots inside the file.
Okay, thank you.
Other questions?
And I guess compaction can be a fairly big task. Does that actually run as a task? Or it's something that the
It runs as an MR job, a MapReduce job in the background. So there's actually 3 threads. There's a thread that wanders around and figures out what do I need to compact and just puts that on a queue. There's the worker threads that actually pick up those requests and spawn a MapReduce job. And you can control how much bandwidth in your cluster that's using by how many of those threads. So the threads only run one job at a time. And so you can just turn that up or down depending on how much you want to do. And then there's a cleaner thread that comes along once the readers are all done and actually deletes the files.
Cool. I'll watch the issue. So.
Awesome. Thank you.
Thank you.
Would you consider, for instance, for simple formats like text file, to run it as a regular HDFS map?
So did we consider text file? So you could do this with text if you used offset in the file as the row ID, basically, but you'd still need something special. You'd need to do a little bit of work to make it work on the deltas, right? But
Yeah.
you could do it. We actually sat down and thought, yeah, you could do it with text file. Yeah, you could do it with sequence file. We're not 100% sure you could make it work with RC file, because we're not sure how you could construct a row ID in that instance, but maybe it's doable.
One more question. Regardless of compactions, do you understand correctly that you use that you do not repack data in org format and simply copy blocks of org, or you do full repack? It's CPU consuming.
We fully read it and rewrite it, but again, it's file format agnostic. So the compactor just instantiates the right input format and the right output format. The rest is pass-through, but
we are doing the same task in our warehouse, and we simply move blocks as the walls because repack is.
But we're
CPU
actually
consuming.
removing contents sometimes, right? If you've got 5 versions of the row in a major compaction, we're actually going to drop 4 of those, right?
We don't deduplicate anything.
Yes.
Okay.
That actually brings up a point that has been asked sometimes, and that's, well, what if you want to keep the previous versions of the data? And actually, major compaction currently drops the old values, but the framework doesn't actually require that. So in the future, we could actually make it an option for compaction, whether the major compaction drops the old values or whether you can go arbitrarily back in time, right? If you want compliance that tracks, okay, if I look back at this point in time, what was the value of this table? You could do that.
Could you actually surface this in Hive? It could work for slowly changing dimensions. I mean, I'm just really making this up right now, but it sounds like a feature, not a bug. So.
You could.
Yeah.
You would have to change the language, right? Because you'd have to have some way to say, give me it as of this time or as of this transaction ID. Where we've had people ask for it is they want to be able to say something like, basically give me the equivalent of a get hash, which in our case would be a transaction ID, when you run a query once, and then you would be able to know, okay, in the future, I can always rerun exactly this query by setting this transaction ID. We could do that. The problem, of course, is that you've kind of got an ever-growing pile in there. You can't really ever clean it up, but maybe you're willing to pay that price.
Well, it's not standard SQL either, so.
Well, go ahead.
No, go ahead.
I don't think we'd be the first people to do it, though. I mean, others have done similar things. This is amusing. It's like a rotating.
Yeah. Okay, I was just go ahead.
But yeah, no.
Who's going to be the last one?
For some tables, I can easily see that the use case would be that you want to store it always back for forever, because it won't be that big, and then you get the advantage of being able to look arbitrarily back in time.
One more question. In case of, you mentioned that you use a sequence generator from metadata store. Typically, it's MySQL. So. But why you don't reconsider and use something like Zookeeper sequence generator? It's not hard, but it can give fault tolerance, because you can write even if Metastore don't available. You can still ingest some data and put some transaction in it.
So you can't ingest anything in Hive without the Metastore anyway. I mean, you can't do anything in Hive when the Metastore is down. You can't even start your query.
We load in data, we put in data in tables and don't use Metastore for that. It's
no,
like
well, you can write into the file system, but you can't
Yeah.
add a partition or any of those things, right? So we're not adding any requirements there. And yeah, you could use Zookeeper to do that, but we've already got a database. It can do it. We already need the database for 15 other things in this, so why add a new tool, right? I mean, Zookeeper adds both install and administration complexity that we just want to avoid if we can. And the reality we see is most people who want fault tolerance or high availability for their Metastore database have already solved that anyway. I mean, there's, depending on whether you Oracle, MySQL, SQL Server, whatever you use, Postgres, whatever you use for your Metastore database, there are fault tolerance solutions for those out there, and people just use them.
Depend. Okay, thank you.
Question, any plans to implement Hive Metastore HA on the application layer?
So
It means you're writing on two Metastores, and if one Metastore is gone, you can use the backup.
right, so the question is any HA for Hive Metastore. That's actually already there. So partly, the database, we just make the database underneath worry about that, because as I just said, there are solutions out there for HA for all those databases. At the thrift service level, that already supports HA. So you can already start two of those and run them, and if one goes down, the other will just take over, and the client knows how to switch between those. So that actually is already, I don't remember if that's 11 or 12, but it's already in Hive. No, you've only got one underlying database. You've got multiple thrift services standing in front of it. Yeah, it's a while ago. Well, see, I lose track. This is the problem of having been on the project too long. But the database itself, as I said, we just depend on people solving that in whatever ways already solved for the database. We don't want to get in the business of trying to do database HA. That's a hard problem, and lots of other smart people are thinking about it. Right.
They can configure like replication between MySQL databases, but if a Hive Metastore goes down, MySQL database goes down, you need to manually switch IP on the.
Right.
It's a kind of pretty big task, but if you are making like the URL, the two hosts, and when you are writing on one host or like kind of like design, it could be we could figure out design, yeah.
Yeah.
So far, it's only one part which doesn't have a chain is a Hive Metastore. Well, unless you invested quite a bit of money.
Right, which is,
Load balancer in front of DC, which is probably makes sense for the busy site, but not for the like.
right, so far we've just said that's what you need to do, is invest the money and, get a database that can do the HA work.
One other piece that I should mention that comes up because it's not obvious is that once you start storing the data like this, that you actually store which transaction last touched the data. And so there'll be some interesting abilities with data provenance to figure out, okay, who last touched this record and what query were they running? So you'll be able to say, okay, this record was updated by Joe when he ran this update query, because the data will already be there.
All right, thank you very much.
Thank you.